Okay, well, welcome everybody. Thank you for coming. My name's John Lakos. I work at Bloomberg, and I was asked to give this talk. It's a little bit of a different kind of talk. It's, if you're expecting to hear the latest and greatest razor's edge on modules, I'm not going to talk about that here. Actually, this talk is very, very old, and it's more about the reasons why we would need modules rather than the sort of the latest syntax and the cutting edge decisions that have been made very recently. So I want to just sort of set the understanding that this is an architectural talk on why we need what modules do, what they don't do, and so on and so forth. I also want to thank Marshall for swapping with me. I had an unexpected event happen, and so I want to dedicate this talk to my wife's late father, Hal. So I'm here, day late, but we're going to talk about some good stuff. So with that said, this is the title of the talk. I'll also mention that the book that I've been promising to have completed is completed. I can finally say that for real, and it'll be out in December. And a lot of what we're going to talk about today is covered in ridiculous detail in that book. So this is just a little bit of a sampling. Put the copyright out because we do that. Here's the abstract, but you don't really need to see that because you're here. So we'll talk about what's the problem. Large-scale C++ software design is a multidimensional problem that incorporates both logical and physical design. How many people feel they know the difference between logical and physical design? Yeah? Okay. So we're going to really get a good dose of that here. We need to be able to isolate functionality in fine-grained physical things, which I have always called components, but we will learn there's another name for them. Requires the designer to delineate, spell out in words, exactly what's going on with this functionality, and when we implement it, we have to make sure that the physical dependencies don't become sprawling or bring in more than they need to be, and worst of all, that they're not cyclic. Anyway, the thing about modules that we're looking for is a more articulate way of specifying the physical properties of software. And so that's one of the things that this talk is going to focus on. But it's going to start with the basics, and it's going to start with something that existed prior to modules that we absolutely needed to do our jobs. So the purpose of this talk, review some basics of component-based design. So here are a couple of the basics that we're going to go through. And a lot of this information was available in my 1996 book, but as I said, the one that's coming up is greatly expanded on. I also have to mention one more thing, which is the reason I'm in shorts against Andrei Alexandrescu's best advice is they lost my bag when I came back. So I literally got off the plane, took a shower, and this is what I got. So my apologies. Anyway, we're going to introduce those concepts, and also we're going to introduce the notion of a module. We're going to do it from first principles. So if you are not up on modules, no problem, because this is old news that's being captured in the module feature of C++ 20. So here's a 4-part talk. I realize there's no way I can give a 4-part talk in an hour and a half, or probably even 3 hours. So we're going to go over the first 2 parts of this 4-part talk. And someday I'll probably finish this talk. The slides are done. It's just more and later. But this will give us quite enough to chew on. So first of all, reviewing elementary properties. This is what I call the fundamental unit of design. It's got logical and physical aspects. The iconography is the round part is the logical part, and the square part is the physical part. And logical refers to classes and functions, and physical refers to files and libraries. And that's kind of the distinction. You get the gist of it. We'll talk about it more. And within each one of these blocks, these components, resides logical content, you see. And a component consists of an implementation, a header, and a test driver. Now, the component itself is the .h and .cpp pair, and the test driver is the one associated with that pair in order to make sure that all the functionality is working as we intended. And this is, the component is the fundamental unit of design. What's interesting is, as we'll see, if you replace the word component with module, not much changes. It's just that modules are better components. All right, so component. What is a component? It's not just a .h.cpp pair. It's got 4 properties. And the first one is that the .cpp file includes the .h file as the first substantive line of code. Now, again, we're talking about pre-module C++. Why is it important, do you think, that we would want to include the .h file in the .cpp file as the first substantive line of code as opposed to just somewhere? And by the way, why do we need to include it at all? Any ideas? To check that it's self-contained. Can you be a little more specific by self-contained?
So if you have includes before, they can influence kind of header, and if you bring out, the header doesn't have to include all the things.
I think what I heard you say is if you include something before, it might change the meaning of the header. That too, but that's not what you were getting at.
I think by including a header as the first thing, you check that it doesn't have implicit dependencies.
Okay, so to summarize what was just said, the reason you have it at all, which we didn't cover, is so that you provide a neighborhood whereby you can check the interface against the implementation. In fact, the implementation won't compile in many cases if you don't have these things that are in the header file. But the reason that it's first is not because the meaning might be different, but because if it is first and it doesn't compile itself, that's a problem. We always want a header file to compile in isolation. Otherwise, you have something called include order dependencies. And include order dependencies are something we've eradicated, like polio, by doing this. So by having them first, you never have to worry about that, including the .h and the .cpp file. Make sure that the header file somewhere compiles in isolation. So this is one technique that we've always used, even if the .cpp file is empty. So we do this all the time. We have a uniform physical structure. And you might want to note that a module represents a uniform physical structure. Regardless of the files, we call it a module, and we call it a component, and they all look alike from a distance, and that's a good thing. The next one, all logical constructs having external linkage defined in a .cpp file are declared in the corresponding .h file. So what does that all mean? So what does external linkage mean? What does defined and declared mean? Does anybody want to offer a quick idea of what it means to declare something? What does that mean? When we declare something, what do we do? You're saying it exists. Okay. Tell it. We introduce a name. So the simple idea for simple people, and it's good enough, is basically a declaration introduces a name into a scope. Now, hyper-technically, it introduces something into a scope, and I learned all of this when I wrote these slides and put it out in the ether and then got lots of feedback. But for a declaration introduces a name into a scope, typically, and as I said, with my experts at my side, I could clarify it and say, well, not exactly, but for our purposes, we'll go with this. It's really good. All right. So is this a declaration, a definition, or both? Declaration and, okay. How about this one? Okay. How about this? How many people think it's a declaration, just a declaration? Raise your hands. Nobody. How many people think it's just a definition? It's just a definition, but not a declaration? All right. How many people think it's both? All right. We see a lot of boths. Anyway, it's both. So what's happening is here, by initializing it, we force it to be a definition. What's this? Declaration or definition? Okay. What about this guy? See, it's tempting to say definition, right? But it really is both because it's self-declaring. What about this? Okay. What about this guy? The beginning of a what? Is this a declaration or definition or both? Only definition? Do I need to declare this before I define it? I might. Well, I'm going to go with this. I'm not sure why I might. Maybe you have some idea that I don't understand.
But you don't have a closing.
Well, I'm not there yet because we're going to have a closing. We're going to get there. What about this? Declaration only. Good. Okay. And what about this? I'm talking about object. Declaration, definition, or both? Okay. And how about this guy? We're all over the place on this one. So it turns out I got it wrong. I got corrected. The real answer is it's both, but that's a useless answer because it turns out that all definitions are by definition declarations according to the standard. But that's nonsense. So we're going to say that this is definition only because if you don't declare it, you can't write it, right? It's not self-declaring. So a definition that's not self-declaring is not a declaration by my definition. And I am against the grammar of C++, forgive me. But I learned that. See, if you go and give a talk and say something that makes sense, you'll find out that you're wrong and no, this other thing is true. And it's not really important because who cares? All right. So int A, what do we mean by linkage? What is linkage? Does anybody want to tell me what linkage is all about? It's what? It's available. It's available is an interesting word. We're sort of going down the right thing. Attila definitely wants to say something. Go ahead, Attila. Visibility of the name outside. I have to think about that one. I'm going to call on Alistair. Alistair, what would you say linkage is?
Linkage is whether you can find that definition outside of that translation.
Okay, so what Alistair just said is the linkage tells you whether you can find the definition outside of the translation unit. And so if something has external linkage, then it can be found outside of the translation unit, to use Alistair's words. If it can't, it doesn't have external linkage, and then it could have internal linkage or no linkage, I guess. So those are your options. But typically when we talk about internal and external linkage, we're talking about something that's a property of the language, not a property of the tools. And it's specifically, are two declarations of the same thing allowed to refer to that thing when they're in separate translation units? Might be another way to say it. Sound about right? He's like going, okay. I trust Alistair's my compiler for truths about C++. So if I say it and he nods, it's good. No, shake head bad. Okay, so we have int A. What is that? Is that an internal or external thing? External. So external linkage. Okay, and I'm thinking about it file scope. What about this thing, static int A? Okay, you guys are good. What about this thing, internal or external? Okay, and this thing? Okay, and this thing? Oh, I heard an external. Anybody think it's internal? You think it's internal? Okay, so once upon a time, a long, long time ago, before C++ was standardized, there was this kind of funny notion about what inlines did, and they didn't work well. And eventually it was decreed that they have external linkage. In other words, just because you make a function inline doesn't change its accessibility. In other words, that's an important property of the language. So it has external linkage, but it definitely has some funny stuff going on. We're going to acknowledge that. What about static, inline, void, blah, blah, blah? Internal. Okay, good. Class foo. No linkage. So the name foo can never be, you can never declare that in one translation unit and have it mean the same thing in another translation unit? That would be unfortunate. We need class foo to be something that spans translation units. So it has external linkage. You're getting the gist of this? This is stuff that comes over time if it's not seeming. What about this guy? Very good. What about this guy? Yay. And this guy? Okay. Does this give you a little flavor for what's going on? These are all language things. It has nothing to do with the tool chain as it's defined in the language. So that is a declaration, and that is a definition. What? Please. Mm-hmm. The class itself exists, right? Once you have the whole, the point, I think what was being said is the class hasn't been, you haven't instantiated an object of the class yet. So your claim is that unless you have an instance, an object of the class, it doesn't exist. That probably isn't true. You can have some meaning associated with something that hasn't been instantiated yet, and then you can instantiate 1, 2, 3, 4, whatever. But what you had before still is there. And there are all kinds of people that write crazy programs where things never get instantiated and still, at compile time, magic happens. Okay. So, how about this guy? What do we think about the linkage? And I'm putting this namespace here, but I'm talking about class foo. What? Okay. And how about this guy? It's inside the namespace, yeah. That's the new concept is we're putting it in the unnamed namespace. Okay? And what about this? Okay? And this? Okay. This doesn't really have, this is one of those things that supposedly just, it's not covered. Did I get that right, Alistair? It's got internal linkage. Okay, see? I've been told now. I've asked this question many times, but I've been told. Slides have to change. Okay. Class, internal linkage. Okay, class foo. You're going to have to explain that to me later, though. What?
No, it's not in the unnamed namespace. The unnamed namespace has been closed.
Okay, back up. What is this, Alistair? Okay. Again, so I said none external-ish. He's saying not external-ish. He's saying it's plain up, straight up external. Okay. Okay. Class foo?
External.
Okay. This guy?
External.
And not Attila. Okay. And this guy? Okay. And how about this? So anyway, the point was something's funny is going on here. And the point that I'm trying to make is that's a declaration, that's a definition, that's a declaration, that's a definition, and that's a definition, and we have multiple definitions. So if we get rid of that, then this works because now I'm defining something that has this definition is for something that has internal linkage. And then if I get rid of that, we're back to not compiling because I didn't declare it, and it's not self-declaring. And so that was the point of that. Oh, I forgot one thing. I have to explain what this rule means. I should probably do that. So this rule, all logical constructs having external linkage defined in a .cpp file are declared in the corresponding .h file. What that means, now that we've learned all that stuff, what that means is if you have something in your component that you are defining, then there needs to be, and its linkage is not local to that component, then it is a requirement of our component-based methodology that there be a declaration in the corresponding header so that we don't have magic ABI things going along under the hood. We want a human being to be able to look at the header file and say, this is being put out into the global ether. So that's what that rule accomplishes. Okay. The third one, all constructs having external or dual bindage, we'll get to that in a second, declared in a .h file, if defined at all, are defined within that component. So I have to explain what bindage is. So linkage is something that's defined by the language, and I want to talk about something else. So I made up a word, as I'm known to do, and the word I made up is bindage, and it has some roots in history where there are things called binders that are a lot like linkers. But anyway, what bindage is it says whether it is based on the typical tool that's used to associate the use of a name with its definition. So if you have internal bindage, that means that the compiler it's the compiler's job to do that association. And if you have external bindage, then it's the linker's job to do that. And if you have dual bindage, guess what? It could be either. So what's an example of something that has internal bindage? Anybody want to throw out a construct in C++ that has internal bindage? So I'll give you an example, a type def. Right? The linker does not get involved with type defs. Right? If you define a type def, it's an alias, the compiler's got to see it. Does that make sense? Okay. If you have a straight C-like function, you have the declaration and the definition. The whole point is to have header files so that you can have a neighborhood where you associate the declaration with its use, you associate the declaration with its implementation. And the idea here is that that function will be associated not by the compiler because we have separate translation units, but by the linker because the use of the function will generate an undefined symbol, and then the definition will generate a definition symbol, and then the linker will come along and glue the two together at link time. Make sense? There are some things in C++ that have both internal and external, or dual, bindage, and sometimes the compiler does the binding, and sometimes the linker does the binding. There are two that I know of. I don't know of any more. What do you think they are? I know you know. Somebody else. What? Templates is one of them. Very good. Somebody else besides templates. What's the other one that has this property? There you go. Look at that. So templates and inline functions, they have very similar implementations. And the way the compiler gets its hands on them is typically when you want templates or inline functions to be used outside of a translation unit, you put them in a header, and then the client gets to see the definition. And then if the client wants to, the client can inject the definition at that point, inline it. Same is true for templates, whether they're inline or not. So that's more and more that's becoming the purview of the compiler to do, although there are some claims that inline, the word inline doesn't do anything. It's just a way of getting it into the header. I don't believe that to be true. We have counterexamples all the time where different compilers will do different things based on the optimization level and so on and so forth, whether something is inline or not. If you say inline specifically in a template, you get different behavior. So we have examples of this. So I don't want to go so far as to say that inline has lost its initial meaning, which is a hint to the compiler. It still does that, but it certainly provides a way of giving the client access to the body of the function, even if it's not a template. All right, so all that said, Constructs having external or dual bindage declared in a .h file, if defined at all, are defined within the component. That is, pretty much, unless you're a class declaration, don't forward declare, and some people will tell you don't even forward declare that. But never, ever, 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 ever declare locally something where the compiler is not eventually going to get to see that declaration along with its definition, because you've lost the benefit of that neighborhood thing that the header file does. And so what happens if somebody makes a change, your client file will continue to compile just like it always did. But when you go to link it, if you're lucky, it won't link, if you're lucky. If it's C linkage, it will link, and then you'll have a runtime error. So that's a very important rule, which says don't forward declare anything that the linker might get its hands on. Does that make sense? That's important. Okay. And then examples of bindage, which I just gave you before, so pretend I had that slide up then. The fourth one is really an important rule for being able to use tools to quickly determine the envelope of physical dependencies among components. And so whenever we have an external linkage or external bindage dependency, if we always pound include, then we will know for sure, 100%, what the envelope of physical dependencies are. If we don't, if we do local declarations, we will miss out. We won't necessarily know what's going on until the time comes when we fail to have this thing around and it fails to link. So this is a great way you can run a script. You can look at the pound includes in the .h and the .cpp, and you can generate a graph, and the graph will be at a superset or the set of allowed dependencies. It won't actually necessarily be anything that is consummated within the language, but it'll be nothing more than that. So that's a good thing. Any questions so far? Okay, so here's some relationships. The next step is to say, well, we have this notion of a component, and then there are logical relationships that are important. And forever and ever, there have been just a few that matter, because you can have a lot of very detailed things, but typically those are extracted from existing code. You don't write them as annotations. When you're designing, you need something pretty simple. And so the first one of these is ISA, and ISA is public inheritance. And so in this thing that I've put here, which is kind of a pedagogical example, we wouldn't normally have what I'll call a value semantic type derive from an abstract interface. But of these things, which one do you think is an abstract interface, or I'll call it a protocol? Shape. So let's assume shape is a pure abstract interface or protocol. And what would be a likely ISA relationship if we're doing, school-like discussions and we're not really serious here? So polygon is a shape, like that, right? Okay, and you'll notice that it's from bubble to bubble. It's not from the box, because the box is representing a physical entity, and this is a logical relationship. Does that make sense? So the next one, because there isn't any other, is what we'll call uses in the interface. And uses in the interface is a property of a function. A function uses a type in the interface if it names it as one of its parameters, part of its signature, or as a return type. So that's what a function uses in the interfaces, and a class uses in the interface is if any of its member functions use a type in its interface. So do we see any candidates here that might possibly use something in the interface? And I'll give you an example. A polygon has things like insert vertex. So what type might we use to represent a vertex? Okay, and so you can imagine that. So polygon uses point in its interface. And there may be many functions that use point in its interface. Does point use polygon in its interface? No. You have to say no quickly. No, of course not. Anyway, no. So that comes quickly. All right, so there are other things that might use point in the interface. Anybody have an idea of what something else is that might be used in the interface? Sorry? Point list, okay. That's absolutely correct. And there's this funny thing called point list underscore link, which also uses point in the interface. Now, this underscore is a special thing in our world, because instead of using nested classes, which have a list of issues that we won't go into right now, we prefer to keep things at a more a shallow level. So a point list uses point list link somehow. But the point list link with the underscore is not allowed to be used outside of the component. So we call the underscore makes it private to the component. And this is by convention. Modules let you do this for real, which is a great thing. So again, here's a case where modules will give you something that heretofore had to be only by convention. But point list uses point list link in another way, which we're going to see now. It's called uses in the implementation. So if something uses something, but you can't tell programmatically that it does, we say it uses it in the implementation. And Polygon might have a data member called point list, in which case Polygon has a point list, and it uses point list in the implementation. But you looking at point list don't see any uses in the interface of point list, right? So we use this black bubble. Uses it, but not in the interface. If I were to change it to be, let's say, point vector or point something else, no clients would have to rework their code. That's the idea. Now, point list also uses point list link in its implementation. No one knows, just by looking at point list, the interface, that it uses point list link. But most likely there are lots of inline functions, so the compiler might know that it's using point list link. But if you're a good citizen, you'll say, it's not my business. I know I've got a point list, and I know it does it somehow, and it does these things. Both of them use point in the interface. So this is all logical relationships. It's always bubble to bubble. Okay. Then we have this other thing called uses in name only. And this is a hard one to get your mind around because it's not intuitive at all. A shape uses point in name only. It's an abstract interface. It consists of no constructors, a bunch of abstract functions that are all pure virtual, and the first function it has is an out-of-line destructor. So that's saying that I can actually compile, link, test a shape without ever having seen the true definition of point. So that's a very interesting thing. It doesn't happen naturally, except for abstract interfaces. And if one really goes after it, if one is trying to exploit this property, it happens in some designs. Okay. So once you have these diagrams, you can infer dependencies. So a polygon is a shape, and therefore a polygon depends on shape. Notice that the arrow is box to box. That's a property of the entire component, aka module. And so modules have physical dependencies that are implied by logical relationships within the modules, also known as components, because they're the same thing, except modules are better, hopefully. Polygon also uses point in the interface. If something uses something in the interface, we must assume that it uses it in the implementation. It might use it at compile time, it might use it at link time, doesn't matter. Somehow, you're going to have to get your hands on that point. And then point list and point list link, that component also, because of the same reason, a uses in the interface relation implies a physical dependency. And then finally, a polygon depends on the point list component because uses in the implementation, certainly, somehow, you're going to have to know what that is. So we can infer all of these without knowing the specific code that caused them. So this is an abstraction. Next level of abstraction, level numbers. It turns out that something that doesn't depend on anything else locally is at level 1, by definition. Something at level n depends on something at level n minus 1, but nothing else higher. So if you look at point is at level 1. Now, interesting question, shape, which has this funny uses in name-only dependency. What level do you think it's at? There are two possibilities, 1 or 2. Those are the two possibilities. How many people think it's at 1? Okay, how many people think it's at 2? Okay, so because of this strange property, we don't include point in shape anywhere. So shape is at level 1. And I can actually compile shape because shape forward declares point, and that's okay. In this particular case, there is a class point, and shape doesn't depend on point at all, strangely. But if you look at point list, that legitimately depends on point because we have a uses in the interface relation. It's not an in-name only relation, and so that causes a change in level number because there is a true physical dependency. The third one, polygon. Polygon depends on point list. It also depends on point. It also depends on shape, but we take the highest one and bump it up one. So polygon is at level 3. Does this make some sort of intuitive sense? Remember that in-name only is a strange special case, and that's why it has the dotted line to remind you that it's not anything other than a collaborative relationship. Okay, so, sure. Yes.
Where you determined the numbers 1, 1, 2, and 3.
Sure.
How did you get to number 3?
The 3 depends on something at level 1, something at level 1, and something at level 2. So it's going to be one higher than the highest thing upon which it depends.
So it had nothing to do with summing up?
There's no summing, no. Levels, literally levels, right? Things at level 3 are allowed to depend on things at level 2 and below. But everything at level 3 is independent of everything else at level 3. Thanks for asking. Everybody good with this? This is kind of super fundamental and important. Okay. So physical design rules. What would you say are the two most important physical design rules? And if you heard me talk before, most certainly you must know. Tell or don't say. What do you think they might be? First one. Like the fundamental, most important rule ever, physical design. Really? Go ahead. There you go. That's the big one. So what's the lesser known but still very, very important rule? There's a second one. In fact, in the book, we call these design imperatives. They're not even rules. They're imperatives. You just can't. What? Sorry. What's the other one? Lesser known but still very important. I know you know. All right, if no one's going to say it, Attila can say. Go ahead. No what? No duplication. No, we do. That's actually a levelization technique. Sometimes we deliberately duplicate things to avoid the first rule. The second one. Go ahead, Attila. No long-distance friendship. What do I mean by that? If you have a modular component, you're not allowed to grant private access outside of that component or module. And I have worked very, very hard with the folks to ensure that modules don't allow such things. And unfortunately, I think there's still some holes where you can, but you'd have to really try hard. You can't just say, oh, you have private access to me. It's not that easy. You really have to go through some hoops. And by the way, you can make something foolproof, but you can't make it damn foolproof. So if people really want to shoot themselves in the foot, I think it's still possible. But these are the two most important rules that I have. So please don't violate them without good reason. And please tell me what the good reason is. Criteria for collocating public classes. So I'm not talking now about something like list link. I'm talking about something that's intended to be seen outside of a component. When would I have more than one such beast inside a single component or module? Anybody have an idea of when that's an important thing to do? They're kind of tied to the two physical design rules. So there's a number one answer. The time you want to have two things in the same component that are both public, friendship. That's the number one answer. So if I have a container and its iterator, the whole point of having the iterator is so that you don't have to expose the details of the container outside of the component in order to extend it. So you do want the iterator to have private access. And if something changes in the container, corresponding changes in the iterator are likely to happen. So you're going to want to change them together, which is another guiding principle, which is keep things together that change together. But here what we're doing is we're exposing a way of extending the container without modifying it. You don't want to always have to go in and add another member function whenever you have a new piece of functionality for a container. Make sense? This is old news. This is like from the 80s, kind of, or at least the 90s. All right. The second reason doesn't come up much, cyclic dependency. This happens more with collections of templates than it really does with plain old object-oriented design. I have yet to see an object-oriented design that really requires putting two components in the same, two classes in the same component. But there are cases with templates where it becomes necessary, and it can become problematic. The third one, this is something that's pre-C++ 11. Before we had variadics, sometimes we would need to create many functions at once that do basically the same thing for a different number of arguments. And no one of them makes particular sense by itself. And so here's an example of what we call single solution. Bunch of logical constructs, no one of them solves a problem. Together they solve a problem. They are independent of each other, but highly collaborative. By contrast, we have a hierarchy of solutions. So an example might be, I have a coordinate, I have a point, I have a box collection, I have a garage. And you can see that they're going up in abstraction, right? Now, someone might argue, wrongly, they'd say, well, I can't have a box collection without a box, so clearly I'm going to put those in the same component. What's wrong with that? Exactly. You can reuse box without collection. You can't reuse collection without box, but who cares? So the idea is, if you have an independently reusable thing, you don't want to tie it to something else that's bigger and more complex. And an example of this that's coming up in the Standards Committee meeting, which I will say right here and now, and is a huge bone of contention even within my band of merry men, is we have contracts, which didn't make it into C++ 20 because a lot of people had slightly different ideas of what some words meant, and among other things. And it also maybe got accepted a meeting or two too early, and once something gets accepted, it's really hard to change it. You need to really have consensus, and that's pretty hard sometimes, especially when it's getting late into it. But the example is this. There's a function called built-in assume. And built-in assume is something that people know they need and use occasionally, whatever, and it's telling the compiler, trust me, this is true. And it's a very low-level thing. You don't use it much. It's a sharp knife. It's down here. And then there are contracts. And contracts are huge. They're big things. And it is true that you can achieve what you can achieve with built-in assume with a fully featured contract system, assuming it's fully featured. Until it becomes fully featured, you can't. And while we're waiting, we have this tiny little thing over here. So the question is, if you knew that in C++ 26, you would have a fully featured contract system, which wouldn't take you that many days to learn, or, and it depends on this. This doesn't know anything about that. Or you've got this tiny little thing here, and you say, you know what? I just want to use that. So then there's that argument. You say, oh, come on, we can have the redundancy because, yeah, this is a little thing here. And yes, if you have this whole big thing over here, you could probably do this. But then there's the other argument that says, when we finally have the fully featured why would you want to use that? Because you could argue in some cases this is better, and the reason it's better is this thing is telling the compiler something that you believe to be true. Have we ever made a mistake? Would you want to be able to just check that that's true once every 6 months to see if it really is true? So anyway, so there's that argument. So we go back and forth and whatever. Bottom line here is if you have something that is tiny, 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 and something huge, 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 the tiny, tiny, tiny thing needs to be independently usable from the huge, huge, huge things because you don't want to drag in all of that stuff. Now, when it's a compiler feature, it's different, so that makes things different. But in the world of libraries, that is an absolute feature. And that brings us to the next thing. This is a bad idea. We're going to separate these into their individual things, and they're going to depend on each other. That's fine. Notice how that's different from the other one. The other one is just, there's no reason to separate it because you couldn't use you'd have to include each one for every problem that you use. You wouldn't just go, oh, wait, I have 4 arguments, and oh, now I have 5. That would be crazy. You just say, I'm including my variadic whatever. Okay, this is fine. The next one, it goes right to the point, which is what we call Flea on an elephant. The thing that I'm describing with the built-in assume and contracts is the thing on the right. The thing on the left is more like a logger with a scoped guard to initialize it. So if you have a big logger, huge, and you have a tiny little piece of syntactic sugar on top, and then you say, I could put it in a separate component, but then when I go to my usage example, and we have usage examples in components, that's one of the big important things is component level documentation, we're going to want to refer to that Flea. By the same token, we could put operator double equals many times in some separate place, but for many reasons we don't. We put them in the same place, even though the operator double equals is a free function, and that free function depends on the object, not vice versa, and doesn't need private access often. We still always put it in the same place because it is a flea on an elephant, and that flea is a useful part of describing how to use it. So again, a flea on an elephant, that's fine. You know, if the built-in assume was going with contracts and you couldn't use the flea without the contracts, that's fine. But you can use the flea without the contracts. The flea is separate. That's the thing on the right. This is bad. Don't do that. And there's an abuse alert, which is it's very easy to rationalize that something that's a heck of a lot bigger than a flea and a whole lot smaller than an elephant are in fact fleas and elephants. So all barnyard animals excluded. It's a flea and an elephant, not a goat and a pig or a dog and a cat or whatever they think. No, it's got to be huge and small. All right. Next topic, insulation. Just checking to see where we're about halfway through. I think we're doing okay. And again, the point here is I'm giving you the background to understand what modules have to do, not what they are. So that's why we're going over. This is very much motivational for how you want to use modules. And there's this thing called insulation. So we have 2 terms, encapsulation and insulation. Does anybody want to take a shot at what encapsulation means? What does encapsulation mean? Hiding the implementation detail. Okay, so that is what it has come to mean, that encapsulation means you put a bunch of stuff together and explicitly hide some of the stuff, typically data. Originally, encapsulation just means putting it all together, but it has come to also imply that you're going to hide something, and typically what you hide is the data. So that's correct. What does insulation mean, do you think? I know you know. No, somebody else. Go ahead. Okay, so keeping modules and components separate from each other, yes, there's something, it's a stronger property than encapsulation. It's like encapsulation with a thickness, not just a paper-thin veneer, but there's actually rubber between it. Okay, so you don't have, I'll explain. So, an implementation detail of a component type, data, or function that can be altered, added, or removed without forcing clients to rework their code is said to be encapsulated. I'll read this again. An implementation detail of a component type, data, or function that can be altered, added, or removed without forcing clients to recompile is said to be insulated. It is a stronger property. In the very bizarre cases where you have insulation but not encapsulation, your design is broken. And there's a section in the new book that talks about that. I think it's 3.9. But anyway, don't do that. So here are these 2 things. And to give you an example of what we mean, here are some components. And I drew this upside down historically for the longest time, but I finally, when it came to the book, I actually drew it properly, and the dependencies go down as they always should, never up. But anyway, here's the client, and here's the library component. And the client is using the library component. And here is an int detail of that library component. And if the header changes, you see that the effect goes straight through to the client, even though it's an int detail of the library component, which means that the library component has to recompile and the client has to recompile. That's unfortunate. On the other hand, well, we say D is encapsulated by C because the client doesn't have to rework the code, but the client does have to recompile. But it's really the use of D that's encapsulated, because anybody could come along and use D. Now, this is a fundamental difference between what we call hierarchical reuse and this sort of Chinese wall, or saying all of my stuff is mine. You can't use it. I can change it whenever I want to, but nobody else can depend on it. The problem with that is you wind up getting an exponential amount of software compared to the software you would get if it could reconverge to a single base of hierarchically reusable infrastructure. So again, it's a different approach. It's the approach that I take, which is hierarchical reuse. And that means that I may or may not be using this thing, but you don't know. So I might change. I might use something else later, but you don't know. But you're welcome to use it from now on because it does what I said it does. It's fine. So say I originally had a linked list and I changed to a vector. You don't know, right? But you could use the list and the vector somewhere else. That's what we're talking about here. Somebody could be using D elsewhere. Now, here's an implementation detail E. C is using E, but it's using it in a way that won't affect its clients if E changes. So here, something changes in the header file of E, but it's included in C's .cpp file. So that has to recompile, and that's it. The client doesn't have to recompile. So that's what we mean. We're saying E is insulated by C. See the difference? Okay. Stronger property. Again, the use of E. The use of E is insulated by C. If I took E away, the client would not need to recompile. Does this make sense? We good? Okay. So, what is the criteria for including a header in a header? Why would we do such a thing? A header file must be self-sufficient with respect to recompilation, right? That's the reason that we put the include first. So why on earth would you include a header in a header?
It's used in header. So the included header contains something that the included header needs for separation.
Okay, so the answer is there is some construct that if I didn't include the header, stuff wouldn't compile. That's basically what you're saying. So there are 5 off the top, obvious, repeatable things that happen. The first one is ISA. If I have a polygon, and a polygon is a shape, every time you got to include, the header is going to include the base class header, and so much so that it's the one transitive include that's allowed. So here's an interesting point. If you include something and it's encapsulated, but because of the way C++ header files work, you get the definition of something you wanted to be private, somebody else can come along and use that. One of the benefits of modules that's super important is that it stops people from coming along and using something that was not meant for them to use. So if you have something private, a real private thing, and you decide to change it, it isn't going to affect anybody else because they couldn't get their hands on it. And yet, if I had a box that was built out of 2 points, but I never exposed point in the interface, and point is not exported, then if a module is worth anything, it's able to provide access to that box and not access to constructing your own points and using your own points outside of the scope of the box that is exported. So is one of these things. That is an exception. Transitive includes are okay. You can assume if it's an is a thing, that's okay. What's another one? Can anybody think of another one? How about has a? So Polygon had a point list. Now, in order for that to work, you're going to have to pound include the point list in the header, or you're not going to be able to. You're going to have not the definition of the type that you need, right? You can't get away with that. So if a polygon needs a point list as a data member, then you have to include it. What's another one? Friendship. That's an interesting one. I'm going to have to think about that. You don't actually, you can declare something that's outside of your component to be a friend, but there's a rule that says don't do that. So we don't want to do that. What?
Yeah, but you might use some component as was in the Lakos.
I'm not following. You might use.
The public component that you can use to make a long distance function.
If it's within the same component. So if you're including something else, that would be outside most likely. Yeah. So what's the third one? What's the third one we might do? Returns? So you're saying like uses. Okay, not uses. I was waiting for some, this is a trap, right? But thank you, you'll definitely get a drink later. But not uses. Yeah, uses are kind of a funny thing. It turns out that just because something uses something in the signature or returns it by value doesn't mean that you necessarily have to pound include it. And so, for example, here, I don't need to pound include point to have this, if you follow what I'm saying, you can just do this. So if I have something in, let's say, Polygon, I could get away with that. And if I don't have point defined directly in the footprint of Polygon, it's entirely possible.
Unless the vertex is in line.
There you go. We're going to get to that. You're on to me. This also, by the way, surprisingly, surprised a lot of people when this first came out. This also doesn't need to be. You need to do it only, as you said, when it's an inline function. So inline function body, yes, that will force it to be the case. Yes, sir. And sometimes, right? It depends on the comment was made and templates. Right? Sometimes templates have to compile a little bit. There are different implementations over the years, right? That are, if you don't use the template, you don't instantiate it, but that's not true of inlines. Templates are weaker, but yeah. Some templates. And then enum, the old C++ 9803 enums. There is a danger, by the way, I'm just going to say it, in the C++ 11 enums, there is a attractive nuisance where you can hide the enumerators. But if you build an enum the way you used to, where you have the declarations in the H and the definitions in the CPP, and now what are you going to do? I want to pass this enum along, but I don't want you to see the enumerators. I got one header, one CPP, I'll just forward declare it. Oops, you can have a different type. You can have an int in the header, or somebody changes the int in the header to a short because it's more efficient, and now the person who declared it locally is going to get bad things happen. So there's an attractive nuisance there, and the way to fix that is to somehow make it so that you have a forwarding header, either as two components or an aberrant component that has the declaration of the type of the integer only, and then the full one that has everything. Slide aside. So enum is another one you can't forward declare, and type def, e.g. to a template specialization. So Sc.D string, you can't forward declare Sc.D string, so you do that. So those are the 5 reasons. And there's some other special edge cases like covariant return types and so on. Anyway, this was the review of this part that gives you an idea of what's going on. And I want to know if there are any questions. And then I'm going to talk briefly about modules, and then I'll try to answer some other questions. No questions? I have some questions. You didn't know there'd be a quiz, right? Think about it. Is there's anything on here that you don't feel comfortable with, ask. All right, while you're thinking, how do we extract component dependencies efficiently? Do we use Clang? What do we do? We grep for what? We grep for pound includes, and if we've done our jobs properly, we can find out the envelope of physical dependencies by simply looking at the edges from one component's .h or .cpp to another component .h, right? Okay. When would we pound include something in a .h file instead of the .cpp file? What would make us do it? Great memory. And the answer is those 5 things, or whenever we would need to in order to make the header file self-sufficient with respect to compilation. Your answer is better, but mine is the covering one. Good job. Last one. What's the benefit or cost generally associated with insulation? Like, what's good about insulation? Less compilation, so more ability to change things. And by the way, to amplify that, it's not just compile time. If you imagine a 3-tiered organization, this actually happened, where you have an infrastructure, middleware, and applications. Imagine the middleware group, it's a waterfall thing, so you build the first layer, then the second layer, then the third layer. Imagine you have a situation where you have either a bug or an inefficiency at the lowest level, and you don't insulate your code. In order to release the lowest level to the second level, right, you do that, to the third level, the second tier has to rebuild. Now, if I just need to do a patch, I can just add a .o to the application and I'm done like that. But if I have to rebuild the world, it could be not even measured in days, but weeks, because there might be regulatory reasons why you have to, when you rebuild this thing, you have to go through some battery of tests, as opposed to being a bug fix, which you can do like that. You see what I'm saying? So keep in mind that sometimes, you know, it's good to have these kind of, and not necessarily complete insulation, but partial insulation. In other words, if just the bits that are really expensive are insulated, or that involve a lot of dragging in of stuff, but not the stuff that needs to be quick, which gets to the other point. When you insulate something, typically, what do you lose? Performance. So when you insulate something completely, you invariably lose performance. Sometimes you can get away with almost no loss by partial insulation techniques. Okay. So the second part, yes. No, runtime. The reason is people have heard of the pimple idiom. Just as an example, that's a total insulation technique on a per module or component basis or class basis, where you say, I'm going to allocate my implementation, and all that's going to be exposed is a pointer. Some people like to use a unique pointer. I happen to hate that because the amount that unique pointer gets you there is very little, and it puts a header file into the thing that's supposed to be an insulating interface, which just galls me to pieces. Some people may do it anyway. But the idea is you're going to do an allocation, and then you're going to do an indirection for every single axis. And so if you wanted to insulate something like an int, now an int is as heavy as a vector. Ugh. But in a pinch, you can do what you need to do. The right answer is always try to insulate things that don't cost you much and are big. So if you have an I/O operation in something that's otherwise all inline, put the I/O operation in the CPP and include all the stuff related to that in the CPP. And just, a stack is the prime example, by the way. Stack is perfect because everything in a stack is inline except that part where you need to go and resize the stack. And you create a function that's private that calls into the CPP file, and then all of your CRUD goes there. And that's, by the way, how you get around that issue when you have a performance defect, like you haven't properly dealt with allocating nodes. You used to allocate 100 nodes, but you realize that's wrong, and you go to 32, and then eventually an adaptive pool. If all of that allocation stuff is in the CPP file, you don't have to wait 3 weeks to re-release throughout the corporation. You just fix it in that 1.0, throw it in, and you're done. Okay, so, yes. Yes. Yeah.
So, I guess if it's all in the rules or the guidance you've given already, then you're only including kind of that when you need to. But let's say you don't do it, don't follow the rules and have
Horrible, horrible things befall you.
accepted dependencies where they're not necessarily needed. Are there strategies for
Oh my dear, what if there's cyclic dependencies? You're in a very desperate place. No, it's the point is to learn this early and never ever deviate. This is the starting point. This is what modules are trying to force you to do. Like, modules were designed in a way that to get around these rules, you have to work extra hard. You know, the gun is like nailed chained to the point this way. You have to go over the thing and like look at the gun on the other side. So don't get there. I don't have any advice for people who have not designed their software, and it's very large, and it's all over. The advice is more along the lines of, stop doing that. Go over here, start writing this stuff, start using this stuff, and eventually this will look like Swiss cheese, and eventually it will either crumble or fall into disuse because you have this nice body of pristine software. And it might take you 5 or 10 years, but if you don't start, you know, you're not going to have it. That's the sad truth. Sorry. All right. So the next one, we're not going to even think about 3 and 4, but we're going to talk a little bit about 2. So I was asked to write this. I was asked something. Somebody asked me something. So I wrote this paper. It's like, I wrote it in an evening. It was 3 pages in ASCII with plenty of spelling errors, and just, this is not normal me, but I had to do it. The spelling errors are. But I wrote it, just had to. And what I did is, it was so quick, I just thought I'd put it up here. This is the paper. It's from July, I think, 2017, Business Requirements for Modules. And again, I don't really care what modules look like syntactically. I do a little bit, but not that much. But if they don't satisfy some of the properties all of the properties that I've described here, they're not useful, and I won't use them. So I basically said, here's what I need from a business perspective, and it's a critical language feature. It has to be able to be introduced into existing code bases, is really what this page is talking about. And if you can't do that, how is anybody ever going to use it? If it works on school projects and that's it, we're doomed. So this is back when I wrote it, so this is my position from 2017 and 2018. We've come a ways since then. So what I'm going to do is say, the thing that I was most scared about is people were using modules as a way of speeding up compilation time. And that has occurred primarily because when C++ started out, it moved some of the work that was done in the CPP file into the header. And that has not stopped. And at this point, things are so compiler-centric that it's almost like the header has become the CPP file, and now we need something else to be the interface because this is what's happened. It's kind of crazy. Anyway, I was worried that if we try to just do this optimization of compile time, and that's all we care about, we might lose some of the great opportunities we have for modules to be something more than just an optimization, but actually an architectural building block larger than a component. Now, I think modules probably are a replacement for components, but they might also someday be a replacement for something bigger than a component. They might be a replacement for something, or another version of what we'll call a package. And a package right today is a collection of components, but there's no way to get a package without getting everything in it. It's like if you have 20 components, package of 20 components is a package of 20 components. we'll get to this, maybe modules can give you something a little more selective, and maybe it can give you different clients a different view on that thing. We'll talk about that a little more. So there are 4 things that I came up with, and I'm saying that I think that are properties of modules that they need to be. And they need to be additive, hierarchical, incremental, and interoperable. And I put here, you can see it's up here, but basically by additive, we should be able to leave a code base alone and just add to it wherever. The hierarchical is when I put something on top, it doesn't change what's underneath. So I can build on top. I don't inject anything into the code base. I don't go in and tweak things to make stuff on top work. That can't be, because whatever is there has a client base and it needs to continue to work as long as it needs to work. By incremental, I mean if I do something in my group, that doesn't mean that somebody else in some distant group has to do something. They don't. They can keep doing whatever they're doing. There's no, I have to do this in lockstep kind of behavior. If that's the case, that will be an impediment to adoption. And then finally, interoperability. And that is, if some people are using modules and some people are using header files, it's perfectly reasonable for somebody to come along and want to use modules to use the module, but they still need to be able to use the header files, because otherwise, unless everybody has converted to modules, the guys that have modules up here won't be able to take advantage of stuff that's really valuable and has been around for a very long time. So that's no good. Now I need to talk about something that has occurred to me. Right now, what do you think modules today do for you with respect to insulation? If something's in a module, is it more, less, or the same compile time coupled? So the example is the case where we had the 5 boxes, and I'm saying if I make a change to something in a module that is exported by the module, something that is the client's compiler can get its hands on in some sense, are we better off than we were with header files? That is not the goal, by the way, of modules. And Alistair, I will turn to you. Do you know of any aspect of modules where we get any insulation effects whatsoever? So basically, there are parts of modules that act as if they're .cpp files that are not exported, but whatever would have been in a header file that's now in the interface of a module is the same thing. It goes through some more gyrations, but if you change it, gets reprocessed, clients downstream are going to be affected. Moreover, the way modules are set up right now, I think, last I observed it, you don't have the embarrassingly parallel situation where you can build any single translation unit anywhere in the hierarchy by itself. You have a set of levels that you have to go through systematically. So we're going to build these things, then we're going to build these things, then we're going to build these things. So you can't even compile them. In other words, you can't put them through their steps. The compile phase has now become not independent, which is different from C and classical C++. Am I right there? He nodded. Good. So we're talking about stuff that changes at, literally every meeting. There's a little bit more discussion of exactly what's what and whether we plugged the holes or not. And at the time I wrote this, I really didn't think it was ready for 20, but I was overruled, which is fair. Let's hope. Anyway. So what I want to do is I think we talked about this this is related to contracts. So for example, if I build something, I might want to build into the module the notion of whether I have contract checking or not. And I want that to be defined not by the client, who happens to include the header file, but I might want to make that a property of the module itself. This was something that we were talking about. I honestly don't know to what extent, we don't have contracts, but I honestly don't know to what extent this is or isn't possible today. I expect in 23 there will be further discussion of this, and we'll have a pretty good idea of what's going to happen when we finally, hopefully, get contracts into the system in 23. The thing that I was talking about, the views, this is an idea that I think is really important. I think it's something that modules can help us with. Often what people will try to do is they will try to provide a different view of a subsystem to different clients. So if you're a steady state business organization and I have this system, whatever it is, I want to provide you a stable view of what's going on. And there may be functions that I'm twiddling with here, and I don't really want you to see them. So in my collection of components and with the methods on the components, I might want to provide you a subset, nothing more, but actually a subset of capabilities that this provides to this group. But there might be a cutting edge group that wants all the changes all the time, and I could give that group a different subset, maybe a lesser subset. But let's say that there's sub-capabilities here that aren't here and some capabilities that are here that aren't here. If somebody were to then use both of these, you would want them to have the union of the capabilities. In other words, there wouldn't be any, they'd all be the same pieces. That's super important for this view kind of thing. So anyway, that's something that I'm envisioning. And if you think about what a C procedural interface is, often when people want to provide something super stable to a C program thing, they'll just provide functions. There's no body, that's the name, it's very well designed, very stable, it's all good. And there, you can provide an opaque pointer to a type. And one of the wonderful things is, if you do that, it's possible for you to then give somebody a C++ compiler on the other side, expose the headers, and the opaque pointers that are coming across are none other than the precise objects that if you had a C++ compiler, you could use. And that's the same kind of aspect that I want this view to be. But there's a tremendous amount of overhead because you're going through functions and allocating whatever. Here, there would be no overhead because the purpose of modules is not to provide that insulating layer, and therefore there's no, thank goodness, there's no runtime overhead associated with modules. That's the good news. All right, so here's an example of a little example that I put together where I have starting out with a library that is header-based, and I have some subsystem that has a header, and I've got this other library that's module-based. And then maybe I want to add something, so I add a module-based subsystem. And this was in the paper itself. I mean, this is how I drew because it was ASCII. And then I have some client that's a module and wants to use both header files, the original infrastructure library, and wrap it all into one thing. And whether it's using the low-level library objects like a date or a time or price or whatever, whether it's using it through some other subsystem that's module-based, or whether it's using it through some subsystem that's header file-based, or whether it's using it directly, that object has the same identity and same meaning. So that's an important goal. If people want to convert, they can, but they don't have to. Now, at the time, I was concerned that Google was using a caching approach, and for people that have lived as long as I have, we know that that happened a long time ago. Template repositories caused huge havoc and didn't work, and so I was concerned. Once we've addressed all of these issues, then it's okay to go on and start to worry about performance. But I just don't want to start I didn't want to start worrying about performance before we captured the big and important ones. These seem to be some of the motivations. Reduce compile time, sure. Eradicate macros, although I got to tell you, whenever you start a new feature, the first thing you do is you model it with macros, you get it working in a production code base, and then you write a paper to the standards committee, and they say, oh, good, we can get rid of macros, and then it becomes a part of the language. But that process starts with doing some experimentation. But we must have a real way to get this into legacy code bases. So again, I'm going to put this up. Here are the 4 things that I wanted to emphasize I think are very important. And, okay, so one thing it does do is it fixes the transitive include problem. So this is a great thing. If we can have the contract assertion levels set by the module, that would be another good thing. Providing multiple views is something we absolutely cannot do reasonably today in C++, so that would be a great thing. And as I said, I want to make sure that clients that get multiple inputs get the union of the capabilities. So here's that picture again, where you start out with something and you're able to build things, and it evolves over time, and maybe we change something, maybe we don't, we add something, all kinds of things can happen, but that's sort of the growth thing that I'm talking about. Don't focus on premature optimizations, because that's going to be not a good thing. Requiring a centralized repository seems like a bad idea. Anyway, these are some thoughts. I think it was too soon to commit to a design, but as I said, I was overruled. So that's my 2 cents on today's modules. It's still to be determined. We have one more standards meeting before modules are set in stone. There are still things going on, and I have a lot of people looking at it. I have people from Bloomberg who are like devoted to the latest and greatest, watching it like a hawk to make sure that we don't at the last second introduce something that would be really awful. And so far, so good. So as a question, what are the engineering requirements for modules? What's important to you guys? What do you want modules to do for you? Anybody have something that they really want from modules? Is compile time speed up the #1 reason in this room? I mean, it's okay if it is. Does anybody just need that so badly because they can't survive without that speed up? Would help. Of course, would help. So we have a would help. Does anybody look for something in modules that is going to make their life better? That's going to be like, now I can actually write C++ code because I have modules, because it does this. What is the this that you're looking for?
Macro isolation from.
So you have, what kind of problems do you have with macros that make you hate them?
So I have an open source library, and I often get issues where people have conflicts with macros defined in like X11 or some other library.
Okay, so after performance, I think the dispatching with macros, or at least having fewer of them, or dealing with them in some more constrained way, is something that a lot of people want. Something, what Attila? What do you think?
I think that this arbitrarily available transitive includes are also a problem. If I want to change my implementation, I use vector for 5 years. I do not want to have vector included for the next 10 years because people refuse to change their code.
So to repeat what Attila said, one of my biggest things that I'm going to be so happy about that's a real problem at Bloomberg is transitive includes. And even if you do something as innocuous as pound include vector, I mean, how bad could that be? But if somebody else was lazy enough not to pound include vector and just happens to know that your thing includes it, and then you want to take it out because you've got something better, you can't, because it will break code. That's horrible. So modules will fix that, and bless modules for doing that. That's great. It's a great thing. So I'm looking forward to that part. But if anybody's looking forward to being able to make changes and not having clients recompile, that's not what modules do. So just know the difference. Know what you're getting, what you're not getting. Yeah?
To what extent do modules really enforce the absence of acyclic dependency? Can you still cheat with
Okay. Again, everything that I have been able to do to insist categorically that cannot happen under any circumstances I have done. And to my knowledge, we have succeeded. Alistair, do you know of an exception? And if you do, don't tell them what it is, because they might do it.
I do my homework. I fear if you're suitably malicious, you might find it.
Okay, so basically, it's at the level of, you really, really, really want to do something really, really, really bad. So what can we do? We can maybe seek mental help, but that's about it, We haven't quite closed it completely. I suspect there's going to be someone who, will make it happen. But
Thought maybe it's out of date information that there was, an exact requirement among the import section.
it's been a requirement from me forever. But, somebody could have snuck something in. You never know. Again, I have people whose sole purpose is to watch for the micro words that might somehow be glued together to allow it to happen. But I sure hope that people get the idea. The reason we don't want it is good. Because when you have cycles, all things are bad. Reuse, testing, understanding, stability, it all goes through it's gone. So don't do that. Anybody else? Because I think I'm pretty much done. Do I have anything else to say? Okay, I could do a quick review of this. Just want to get this out here. Component is the fundamental unit of both logical and physical design. No cyclic dependencies or long-distance friendship. You remember that? We want to collocate constructs only with good reason. Friendship cycles, part of a whole, or Flea on an elephant. There's a wonderful cartoon of a flea on an elephant in the books, by the way, if you want to. Just for that, you should get the book. December. You put an include in a header only with good reason. ISA has a inline enum and typedef. ISA has a inline enum and typedef to a template. Remember those. Otherwise, don't. You really don't want to have includes and includes because you are causing all kinds of churn. It's not just compile time, it's compile time coupling. That's more than just compile time. And that's the end of that. So if anybody has any questions, I'm still here, and we have 4 minutes, but I'm basically done. Yes? It is. Okay, it will be a first iteration. I suspect we'll find things. It is in way, way better shape than when I wrote this paper, for sure. For sure. So, it's not known to be a disaster. There is a concern about tooling. There is a concern about how do you map the module locations? How do you find them? How do you know where things are? I'm going to be very interested to see how that pans out, but there's definitely the biggest unknown is how is this tooling going to work? Because some things that have been suggested just are like, you have to be kidding, like that. But we're getting better. Latest I heard, I was there, when I say there, I mean here. I've traveled like 10,000 miles since then. But seriously, when I was here, I heard good things the past week, so I'm hopeful. No, not, well, you say immediately. Again, I doubt immediately. Alistair, any chance that it'll be there for 23? No, libraries with modules. Yes. Okay, you heard it from somebody who was a previous library working group chair, so that's a much better indication than what I would know. I'm skeptical of lots of things, but, supportive. Okay, one more, Alistair.
How ready are modules for 20? If we think into faculty for 28, how ready were templates? We had a grand, useful facility. If it stopped there, we had enough, it's a great thing, but we could make it better. And I think that's where modules are in C++ 20. They're a great, useful thing, but we also imagine there might be things to make them better in the future.
So just to repeat what Alistair said, in 98, we had a template facility, and we continued to grow that in 11, 14, 17, and 20. Modules are starting in 20. Contracts just missed it, but contracts will be something good in 23, and it will be already a step beyond where it would have been in 20, because we came really close to getting that right, and we will get it right 100% because we've got all the people involved. We have our own study group. We're being very polite, and we're gonna get everybody's needs met without it looking like a mess. But there's some definite things. All right, well, I guess unless anybody has something burning to say in the last minute, I'll thank you all for coming, and Have a great rest of the conference.